There's lots to do on it.
Yeah, you can do all kinds of stuff with it.
Yeah.
So we'll get you started on that. All right. So let's review real quick what we have going in here. Kirchhoff's voltage law, Kirchhoff's current law. Again, we won't, here on out, you don't have a lot of reason to solve circuits using those strictly. You're probably going to instead use, if it's a resistor network with a single source, rather than doing that stuff, you're going to just reduce using equivalent resistors, series and parallel resistors, and simplify it down and find your voltages and currents build back up. But these are still critical to always keep in mind because they're a way to check how things work. You always know that the voltage law says if I go around any loop anywhere that makes a full circuit, all the voltage is summed to zero. Or all the voltages in equal all the voltages out. Current law says if I'm in a junction, all the current in equals all the current out. From there now, though, we can use mesh currents to solve problems. We can use nodal voltages to solve problems. And the truth is that there'll just be some problems one of those techniques solves easier than the other. And it's getting to know them is really just working through the problems and usually get a little bit of an indication. But there'll be mesh currents where we have, we need two current equations, or we can do one nodal voltage. But there are other times currents are a lot easier. With bridge circuits, currents are typically the easiest way to do it. So you should be able to use both. Again, nodal voltage is the most important thing in a way of that. So recognize all my software uses that. And if I have a schematic that has a bunch of test voltages listed on it, those are all essentially nodal voltages because you're going from that voltage to ground. So if it just says VA at some point on the circuit marked A, what it means is measure that voltage compared to ground. And most likely that ground is the metal chassis it's sitting in, or it's the little ground connection, or the power ground coming in. You just put the ground there and then stick the other up on that spot, measure that voltage, and I'll tell you what that would be. Calculation-wise, I'd say they're about equal. It just depends on the problem. You do end up with fractions here. You have to get rid of the denominator. You don't end up with fractions here. So sometimes that's easier. But we worked on multiplying fractions. Okay, the term superposition. In general, superposition means it's any mathematical thing, mathematical problem where I can take two different things that are in it and say I'm going to work all for A and I'm going to work all for B, and then I'm just going to add everything together. So for us at this point for DC circuits, it's going to apply when I have two or more sources that can either be voltage sources or current sources. I remove one and I solve everything for the other. I put the first one back in and remove the second, solve everything, and add my voltages and currents together. Make sure you keep your polarities in mind there, right? You might end up with a 5 volts plus to minus and a 2.5 plus to minus, which means you end up with 2.5 overall on it, not 7.5. You gotta keep track of your polarities in your current directions, which is polarity. If I have a voltage source, I replace the source with a short. If I have a current source, I replace the source with an open. This is a pretty much standard issue, by the way. You replace one way and the other you do the other way. In reality, most things we use, we treat as voltage sources, but we do have current sources. These power supplies I bought that we use on the bottom, you can use them as either a voltage or current source. That's why they have both controls. That's why you have to turn both. You have to turn both up, though. You notice if you just turn voltage up and current all the way down, it won't do anything. You turn the current up, it'll limit what the current will be, and then you adjust the voltage. Or you turn the voltage up, and then it'll limit the current, but allow the current to go to a certain point. Okay, these are big networking approaches to solving problems. So hopefully we have all those down because we're done with them. And if we don't, you need to talk to me and get help on them. Make sure you get the homework in the labs. 2 weeks from today, we'll have a test on them, and guess what will be on that test?
that stuff.
Yeah, there's a good chance. We'll see what I do in the end for next week's material. But everything we've covered since the last exam has been this. So it's very tempting for this just to put 5 problems on it that make you go through and do this, today's stuff, and then maybe one other thing. Next week, we will go through it. We're going to go back and revisit some stuff we did in the 108 class last fall. Batteries, conductors, conductor resistance. I think hopefully it comes pretty easily to you. In fact, if you look ahead, if you get time, look ahead and read it for next week and see if you can do the homework before you get there. You might come in and say, yeah, I've already got it, because it's mostly just taking stuff where I did last semester. And I just dive into doing a little deeper calculations on it. Lots of those nice tables that you have in your text. So I don't know if you remember the ones that showed like conductor size and conductor diameter, gauge number, diameter, blah blah blah. Figure out the voltage drop if I have a 1,000-foot run of this size of conductor. Find out what's my power delivery. I think it's worth really revisiting that now after we've looked at more bigger real world circuits of how does this really impact things. You have a better reference. But it's kind of totally different than anything we've done to this one. All right, then, like I said, 2 weeks exam. Keep in mind, you come to the exam, you get a full equation sheet as normal, you get the calculator, you get a writing utensil, or 2 or 3 or 4 or 5, you get a brain, you don't get one of those. I just joke that. There's a physics lab at Hampton that's working with the hot cooker when you get water boiling. He always had lab equipment written on it. The last one, that was a brain. Okay, what's today? Thevenin. Equivalent circuits. Okay, Thevenin and then later Norton equivalent circuits are concepts and techniques that we will carry forward, much like we carry Ohm's law forward and we carry Kirchhoff's laws forward. It has a lot of applications that go beyond this class. There will be courses next fall and next spring where I'll say, here's the Thevenin equivalent of this, or calculate the Thevenin equivalent of this.
Yeah, I think we had a lot of this on our last week's.
Yeah, you might. I do have sometimes the homeworks. I'll have stuff like last week's, knowing that we're going to cover it this week. It's like, okay, if we hit it, this
yeah,
it's okay. It's also not hard on. So, what we're trying to do is we're going to replace the resistance of the circuit. Actually, let me write it. I'm all right. We're going to find a single voltage source and series resistance. I don't call it series resistor. That are equivalent to the entire circuit. Except the load. So we'll treat the load as its own thing. So what I'm going to do in the end is I'm going to end up with this. I'll end up with a voltage source, and I'll put TH for Thevenin. It's very common to see those written as TH, THE, V, or something like that. Maybe the whole thing spelled out in some script. A single resistor. And then we typically leave this open when we're all done and just write load or something like that in between there. Now in reality, to form the circuit, we'll put the load. Here's the goal of this, is to say, you know, in most circuits, I have something I'm trying to provide to a load, and that load might be a motor, a light, a computer, just another resistor in these early cases. Whatever it is, it can change over time. So if I have, you know, a load here that's 1 ohm, and then I replace that load with 2 ohms, I'm going to draw less current. If I reduce the entire circuit down to this single voltage and this single resistor, then that means I have a really simple little series circuit. I can just swap that load out. So the idea is I'm not replacing it. The other stuff is just part of the static, and I can replace this load part. All right, so here's how we do this process. Remove the load. And I'm going to say for now resistor because we're talking about DC circuits. This is one of those, as a standard, it carries forward. So in reality, once we hit AC circuits, we'll go back and do Thevenin equivalents, which it could include capacitors and inductors. Again, it could be some other load here, like a motor or something. But remove the load resistor. Open across it. So if I remove it, I want to make sure I'm not shorting it. I'm removing it, and it's an open circuit there. I remove my voltage sources. And I make those short circuits. That's why I could specify. So wherever that load was, maybe I shouldn't put our load because it's not a resistor. So I remove that load resistor. Those two spots, after I do this with those sources, I'll find the equivalent resistance from its perspective. Like if I remove everything, I can measure it. I can do this with a real circuit, right? I can pull the sources out short. Do not short across the plugged in source. Remove it and short that area. And I can remove whatever is my load resistor and just measure the resistance there. I can do my calculation. Okay. Actually, I'll probably do these opposite order, but find the across the load. Find the Thevenin equivalent voltage across the load. Okay, so what I'm going to do, let's do this example. This is from your text, by the way, so you read the text, this exact example. So I'm going to repeat this example we've used before. Four, two, one, 28.7. And wow, I need to figure. That look familiar? I've used that exact same circuit for my other networking theorem problems. Okay. Step 1. Remove the load. I could make any resistor here the load I want. Presumably in a real problem, it's clear what the load is, or sometimes we're just told to find the Thevenin equivalent from a perspective where it's just an open spot with load we can connect. So in this case, I'm going to make the load the 2 ohm resistor. So this is the load resistor, and that means that's what I'm trying to provide voltage to, or that's the one I can easily replace and put other resistances in. All right, so I'm going to remove that. I'll do this very step by step. I would skip steps here once I got going. I'll draw those just to show, hey, that's where the load is. Load. That's not too bad. Now what do? Well, I had 2 choices. I need to find the voltage crossed here, and I need to find the resistance crossed here. So what I'm going to do, is, like I said, I'll do these in the opposite order. Is I'm going to go find the voltage first. Right behind the monitor, isn't it? So let's find the Thevenin voltage. That's the voltage between here and here. Did I screw up?
You put the ohm symbol on the sources.
Oh. I'm glad you're awake. Obviously, I'm not. Yeah, I did not mean to change that. That was not part of the intended process. All right. So how do I solve this? I have a loop. This is an easy loop. Man, not a trivial loop, right? But it's a loop. So I'm going to go around the loop. So Kirchhoff's voltage law, my loop, I have 28 volts in. I would have a current. I'll just do a current in this direction. Minus 4 ohms times my current. Minus 1 ohm times my unknown current. Minus 7 volts, because that polarity is opposite of this one, right? This polarity is positive up here and negative. Positive and negative. The way I wrote these, of course I'm going this way. I drew that current to go like this, right? I didn't switch up my colored markers here for when I'm solving. Does that actually help? I'm sure it's just as clear. All right, I will drop my units up here just to make the math. 28 volts minus 7 is 21. Minus 4 minus 1 is minus 5. Enjoy one of our few times we get to use that. Oh, that's not as bad as I thought it was gonna be. Yeah, what I was saying, one of our times we get to use actual amps. Everybody good with what I've got up to this point? Not too bad, is it? So now I need to find the voltage. So let's find voltage drops. So the voltage across the 4 ohm, it's going to be that current, 4.2 amps, times 4 ohms, which is, what, 16.8? Right? Yes, 16.8. Voltage across the 1 ohm is 4.2 amps times 1 ohm, so yeah, pretty comfortable. It's 4.2 volts. So I'm gonna come back here. I'm gonna go ahead and switch the markers up. I should have done that before, just to mostly to keep the picture a little clearer. I was close. So I'm just gonna erase the little bits I added on here and start solving the problem. Then rewrite them. So when I started the problem, I recognized the polarity of my batteries. I decided the current's gonna go that way. So I end up with 16.8 volts, 4.2 volts. So at this point, I've taken 28 volts and direct drop 16.8. So 28 minus 16.8. That's relative to here. I can also see the other direction. If I just look here, I got in 7, 4.2 would be 11.2 volts, right? Either way, I end up at 11.2 volts. And that voltage is what I want. So I'm all done. This Thevenin voltage, I started right at T. It's 11.2 volts. Can I erase my other board now? Does it seem right to you? Have any idea? This right here. Now I'm going to rewrite the circuit. Let's find the Thevenin resistance. So I have my 4 ohms. I replace this battery with a short. I have 1 ohm. I replace this battery with a short. So what I'm looking for is the resistance between here and here. If I were to measure, what's that equivalent resistance?
It's just 5 ohms.
It's not, because I'm measuring the resistance between here and here. So if I take a look at my connections, this is all connected. These two sides are directly connected together.
Parallel.
So I could take this and just redraw this. And I remember I just kind of scooch my batteries where, oh, my batteries too. Anything in the schematics, remember, because they're all about connections. Yeah, so this is actually parallel. So 1 over the equivalent equals 1 over 4 plus 1 over 1. Be careful, it's not 2/5. We hit the fractions. Yeah, go ahead.
Over there, how did you get 11.2 volts?
I did 28 minus 16.8. Because if I start from this end, which is this side, I get to go up 28 and I drop 16.8. Or I can go from here and I go up 7 and I go up 4.2. I both end up with 11.2 volts.
Where'd you get the 16.8 at?
I found the current. I found the current, and I just used the current to find those 2 voltages. All right. So is that 0.8? Seems like 0.8.
Yeah, 4/5.
So this is what this means and what Thevenin equivalence does for me. That entire circuit we built the Thevenin equivalent circuit is 11.2 volts, 0.8 ohms. So what this says is that this original circuit up here, we say, hey, this is my load. So that's this 1 ohm and 4 ohm are built into the circuit. Maybe that's the internal inherent resistance of those 2 sources. Those are very high values for that, but just conceptually, maybe that's what it is. And I have 2 sources. And remember, we've gone around and around with 3 sets of networking theorems over the last 3 weeks trying to deal with problems like this. And it's perfectly good to solve that problem at one time. And you have to go back and redo it and put in new numbers to solve it the second time. And you have to put in new numbers and resolve it the third time. The beauty of that is you learn how to solve it. The negative of it is it just takes time doing algebra every single time. And guess what? We're engineers. We're not mathematicians. So we don't like sitting around doing math that's unnecessary. We only do the math that we have to. So I'm going to reduce that entire circuit down to a single equivalent source and a single equivalent resistance. Those are the Thevenin values. If I would like to now, I can take that original circuit, take my load resistor, put my load resistor in, because, well, it's not really a circuit until I add a load resistor, right? And the load is the initial 2 ohms. But now I can change that to anything I want. I can say, oh, hold it, I found a new one. It's got less resistance. I'll put a 1 ohm in there. Now I don't have to resolve the whole problem. I can just have a simple series circuit. So, with my load at 2 ohms, I can find whatever I want, right? The current in the circuit, according to Ohm's law, is 11.2 volts over 2.8 ohms. Right? Just take this voltage over the total resistance. 11.2 volts over 2.8. 4 amps, which I believe is what we got in all the other problems, just like this, that are with that same circuit. The voltage across the load. I can write load if I want, since it's a series circuit, same current. The voltage across the load is 4 amps times 2 ohms. It's 8 volts, which I'm pretty sure is what we found before when we did that problem. First time, 3 weeks ago or 4 weeks ago, and then 3 weeks ago, and then 2 weeks ago, and then last week. I remember if we did the exact same one board, but your text uses the exact same problem every time, and you can see how it works different. The process. You have questions about it? here's the beauty of my Thevenin circuit now. I can very quickly go through this and try a whole bunch of different load resistors. Since nothing else is changing, I solved it once. I'm going to erase this bit over here on this board if that's okay. Are you up with me, Danielle? Or are you still over here?
So it's at 28 minus 16.8, and that's how you got the 11.2.
Yes.
And then the other way is 7 plus.
Yeah, you don't watch the polarity. So here, I go up 28 volts, then I drop 16.8 volts.
And then the other way.
Other way, I would go up 7, I go up 4.2.
Okay.
All I'm going to do here is go through and solve the first line or so of this. Actually, the third line in. What's the power? Current times voltage.
32.
Watts. So for the 5 ohms, or 0.5 ohms, I should say, current equals 11.2 volts over 1.3 ohms, right? 0.8 plus 0.5. I drop this 11.2, 1.3. 8.615 amps. Voltage across the load is 8.615 amps times the load resistor. A little over 37 watts there. For the 1 ohm case, 11.2 volts over 1.8 ohms, right? So I'm always going to take that resistor plus the Thevenin resistance. You guys good with those two? I'm going to go down and do the rest without writing it all out. So to get the current here, I would take 11.2 divided by 5.8. 1.931 amps times 5. 9.655 volts. Of course, you could use, if you just needed the voltage, you could also use the voltage divider equation. You notice all those things we arrived at this semester, they're really just going back to Ohm's law and Kirchhoff's laws and finding different ways to do them. So, oh, I know voltage divider equation. If I need voltage, I'll just use it. Multiply the load voltage, our load resistor over the combined resistor times the voltage. Okay. Why did I do that entire table? Because I like doing lots of multiplication and division? Nope. Do you know some trends here now? This is like I said, one of the advantages of Thevenin equivalent is now that I have it, I can really quickly go calculate all these different loads. I can look at the other things. What happens with my current as my resistance increases?
It decreases.
Yeah, I mean, is that a big surprise? No, hopefully not. What happens with my voltage as my load resistor increases?
It increases.
So I increase my load, the voltage across it goes up, the current across it goes down. Hopefully that's no surprise. That seems like a real Ohm's law and resistor equivalent resistor. However, the power is interesting. What happens with the power?
It goes up and then back down.
Yes. So power, maximum power to the resistor doesn't steadily go down. Starts here, it starts very high, but it goes up and then goes back down. Where do you think the maximum power delivery will be?
Probably right around 1 ohm. Like in between 0.5 and 1 ohm.
That's exactly, I mean, it's got to be in there. There's actually an exact amount it will be, and I know what it is because, well, I guess I'm teaching this. But it will actually be when the load has the same resistance as the Thevenin. So I probably should have put that in the table, and I thought about it after looking at it. Maximum power delivery. This is actually a general truism for circuits. It's something I can ask about now that you've seen it and I demonstrated. 0.8 ohms. The maximum power delivery I can have to something is when I make sure that the load resistance is equivalent to the Thevenin resistance. So this Thevenin thing is really important because I can switch the load real quickly. And it's also really important because when I found the Thevenin resistance, I know what I should set my load at to get the maximum power delivery. And a lot of times I'm really not about maximum current or voltage, I'm about maximum power delivery. I'll take the power created by my source and deliver it. This has some interesting side effects. My actual cables that we'll be talking about next week and how much power they take out. If I want absolute maximum power delivery, I need my load to be the same resistance as the resistive loss I have on the cables that deliver voltage current. You might think, when you think of them as being zero, it might be tempting to think, well, my resistor, but I do want my resistor small because it maximizes my current. Makes my power highest. So let's work out. So let's go try this real quick. What's the current here if I do this? 11.2 volts over 1.6 ohms is the number 11.2. Oh, isn't that? Did I expect it to be a nice neat number? 7 amps. Voltage across the load. 7 amps times 0.8 ohms, 5.6 volts. Power at the load, 7 amps times 5.6 volts, 39.2 watts. So the max, so I can ask various questions on this, for example, in the homework or the exam in 2 weeks, or whatever else you want. What's maximum? I could deliver that initial circuit and say, hey, what's maximum power delivery? You can, replace R whatever. What R would give you maximum power delivery? You go, oh, I got to find the equivalent, the Thevenin equivalent voltage, the Thevenin equivalent resistance. and then put that resistance in. Power here, it's a little over, it's actually, it looks like it may not break 38 point something, but it's actually a little over 39 watts I can provide when I put a 0.8 ohm out there. Okay, so we know Thevenin equivalent. Lots of homework this week, and a whole lab doing Thevenin equivalent, because when I get to lab, what do? I can go in, I can build that exact circuit, and then I remove the resistor and measure the voltage across it, and I have my Thevenin voltage. Leave that resistor out, remove both power supplies completely from the system, and then go in where they were connected and put shorts on there. Once the power supplies are disconnected, I can't emphasize that enough. Once the power supplies are disconnected, do not short them while they're connected. And then go back and measure the voltage across, or the resistance across those two and get the equivalent resistance. If I built this exact circuit, I should be able to do all that. I won't, because it'd be like high power resistors. But you'll do that in lab. You'll go in and do, hey, let's do these calculations, let's come up with values, and let's put it back in and see that it works. Anything with maximum power transfer, you can do that too. Look at that. One nice little short 50-minute lecture. Look how much we learned. Very practical. None of it's esoteric.